All right, so it's time to train our model, right? Let's say that we've gotten our data where we want it to be. We pick the technique, we're clear about the outcome that we're striving for, at least, right? So let's talk about the different algorithms that we can use. There's going to be some really interesting charts here that you probably at least want to take some kind of like notes or screenshots of. Obviously, these are inside your student guide as well. And we're going to talk about different kind of like validation techniques that are appropriate here. And then of course the simple holdout, like splitting the data also, and different kind of like how to run like training jobs. And of course it probably will be tomorrow because I believe we're gonna run out of time before we get there. But I'll create a simple training job actually in the console so you can see it set up. So let's talk about algos. So the goal of training obviously is to create an accurate model that answers the business question correctly as often as you need it to or more. So choosing the right algorithm for that is obviously important. Amazon SageMaker has 17 built-in algorithms that you can use, but you can, if you use an existing framework that they already support, you can bring what algorithm you want. If you want to change the framework and the algorithm, you can do that, or you can actually get a third-party one from the marketplace if you prefer something else along those lines. Now, obviously different algorithms are optimized for different things, right? So, something that you would use for forecasting wouldn't be the same as you would use for binary classification. So question is what problem do you need to solve, right? So for example, in general, right, because a lot of the algorithms actually have multiple purposes or multiple uses, and have tons of different like flavors and objectives that you can set them to. Hold on just one second. So when it comes to classification, right, so linear learner, right, could be used along with XGBoost to do just simple like binary classification. So this is a general guide. Now I will tell you, I think this is in the student notes. Let me see here. Oh yeah, here it is. A really good reference for this is actually this particular doc, which I just pasted in chat, which will tell you basically an example problem, the problem types that it can solve, the data input format, right, in this particular case. Notice text, tabular data, or images, right, for this in this particular setup. So this is also kind of a great table. You will have to, honestly, you're going to have to know this. It is going to come up on the exam. They're going to test your knowledge about it. They're going to want to know, when you would use factorization machines versus KNN versus linear learner versus extreme gradient boost, right? XGBoost. They are going to test, right, whether or not you know that. Now, luckily, there's only 17 items here, so you just learn them by bucket by classification, right? Learn the supervised learning ones first. They can go for unsupervised learning, and then take a look at the textual analysis and the image processing. So they're going to test whether or not when to use semantic segmentation, like, if I kind of what's happening right now with blurry, not blurry on my Zoom video, right? Whether you can detect objects when you would use that. They're going to test all of that, right? When you would, yeah. Anyway, this particular table is going to pretty much capture everything you need to know, both how to use SageMaker and, of course, for the exam itself. So supervised learning, so classification is going to focus, well, yes. I don't know about recommended instances, but you're going to need to know that which data types they take, right? Whether it's structured data or just raw text, or whether it's images and videos, that's pretty much what you're going to have to know. You're not necessarily going to have to be able to rattle off all the different file types that they take. The only one they really test you for is knowing that Athena takes Parquet as this optimized data set, and that SageMaker takes Protobuf as this optimized data set. So that's pretty much the only like kind of file types they generally challenge. They might like want you to know whether or not you can take JPEGs, with certain algorithms, but like, that's it, right? That's all I really check on. So protobuf is the fastest of the tabular data types for SageMaker, and Parquet is the fastest for Athena. So knowing, like, for multi-class, right, and regression, which ones you're going to use, KNN, nearest neighbor, or XGBoost, knowing that regression could engage a variety of different algorithms, and that recommendations could be based on factorization machines, or it could be based on other things. So this is mainly for supervised learning. For unsupervised learning, they're gonna, can you do topic modeling? Can you do generalized clustering? So for k-means or LDA, and then can you determine embeddings? Can you do anomaly detection and IP dimensionality reduction? They are going to basically test, like, do you know how to use these unsupervised algorithms? IP Insights in particular, by the way, I remember they asked 2 questions about testing to see whether or not I knew that they could use IP to detect anomalous like behavior. Random Cut Forest, by the way, runs inside SageMaker. It also runs inside of Kinesis Data Analytics. So you can actually run, do anomaly detection on real-time streams. And so they're going to test little things like that. And then, machine translation, word to vec, text classification, topic modeling again, right? Notice that with this text here, topic modeling with LDA and then NTM, and then speech, which is sequence to sequence, and then images and video and time series. Now, time series forecasting, if they start asking you about time series forecasting, it's pretty much for them, it's always going to be DPAR. Again, it depends on what's in the answer set, but usually DPAR is what they're looking for. And then they don't ask a whole lot of questions, at least not on the exam that I saw or any of the practice exams that I've seen, about ResNet or VGG or PSP or FCN. They'll ask you about semantic segmentation, right? They'll ask you about object detection. They will ask you about image classification, but for some reason they don't really call out the algos behind those. Not sure why. So yeah, pull this out of the way. So this contains, these 4 slides are going to contain, in general, plus the link I just sent, the algos that you're really going to want to like memorize and pay attention to. I can't remember what the total number is, but I think it's 17, if I remember correctly. If it's still accurate based on here. Yeah, I think it's still about 17, actually. So a lot of the practice exams, by the way, are going to force, like, realign your knowledge. So when you do the practice exams, they are definitely going to test and challenge whether or not you know these concepts around, image classification, object detection, semantic segmentation. They're going to make sure that you understand what the underlying algorithms are. So again, I didn't see a whole lot on ResNet, but that may have just been my exam, actually, also. Now, there's a lot of different data formats that could be supported. When I say a lot, there's like 7 actually. But mainly for most of the built-in algorithms, CSV and protobuf are going to be, for the tabular ones, right, are going to be the ones that are going to be supported. You can do pipe mode with CSV and with protobuf. What's interesting is that I got the distinct impression from the exam that they didn't really think that CSV could do pipe inputs. So that threw me off just a little bit, because I was like, I kept getting questions where it was like, they were basically implying, I know through the nature of the question, you were getting this sentiment that somehow CSVs couldn't handle pipe output, which it can, it has for years, actually. Yeah. Record IO protobuf seems to be the preferred structure, which I understand because the performance is greatly improved if you do that, just like with Athena, if you use Parquet. But some of the questions were like, huh, really? You don't think CSV can do pipe? It can, actually. Yeah.
I have a question. If we like go back to the SageMaker algorithms, so is that essentially saying that those are the algorithms or like packages that we have to use? Because I did notice on recommendation, like system example class thing that we're doing, that we were to use a factorization machine, which I guess we're going to do yesterday instead of another technique. So if we're in SageMaker, will we have to use one of these?
Yes, these are the algorithms that you have to use, and yes, you decide to either define your own script to change the algorithm, either use, scikit or imbalance learn or whatever, or if you want to bring your own Docker container.
Oh, okay. Because like, I don't know, I work with text a lot, so I was looking at that, so I'm more familiar with it. So if I were to use like Blazing Text, because that's built on top of like Word2Vec, does it only contain like skip trans and like continuous backwards, or could I also have like Doc2Vec or anything else that's within like GenSim?
You'd have to dive into the documentation to answer that, Darcy.
Okay.
Yeah. So, but these are the algorithms that you're limited to, if that's what you're asking.
Yeah. Okay.
Yeah.
All right. Thank
Now,
you.
as far as the variations of those, right, you have to look underneath the specific documentation, because like XGBoost has got a number of different objectives that you can set for that. So you can look for the subtleties there. But I would dive into the Blazing Text documentation if you're looking for something very specific.
Okay. Yeah. I just didn't know because we can. So essentially, the only 5 essentially packages we can import are like pandas, NumPy, scikit-learn, and then the other 2, and then these 17 algorithms.
No,
No.
you can import whatever you want to,
Okay.
right? So you anything that's in Python code or that will run in R or Julia, you can import anything you want to into SageMaker. If you want to use the SageMaker SDK and call something against the SageMaker API and have it run, it has to be one of these 17 algorithms. If you want to write your own, right, you can execute that as well, right? But just know that if you're going to actually call the API and have the API execute against the data set and return the prediction for you, you're going to need to use one of the built-in algorithms, right? Again, you can actually, if you want, shove your own Docker container in there and still call the API, but you're going to have to do some custom work to either get the algo changed or the framework changed. The framework is the one that requires a Docker container change in order to execute. So you can use the built-ins, but if you want to customize it, you're either going to customize it in code or you're going to do it both code and with a Docker container. And at that point, you could call the SageMaker endpoint. Does that make sense? Sounds like I just confused you.
Yeah, I'll just wait to see how the rest of the how the rest of it plays out and see if like all pieces together.
Yeah, don't worry. Well, you'll see a representation of what your possibilities are as far as the algorithms go. But these are the 17 built-in ones.
Okay.
Okay.
Yeah. Thanks.
All right. Sorry. Other questions? Okay. One thing that's kind of worth stating is that for SageMaker, for the built-in algorithms, the label in your training set must be the first column on your left, and your features, oddly enough, ideally should be the right. So your like outcome that you're trying to predict should be the first column on the left-hand side. So it also requires, by the way, the CSV file has no header. So it says that, by the way. I know for a fact that some of the algorithms don't like that. So, but by default, labels are on the left-hand side, first column. So that's just general CSV formatting. If you're doing protobuf, right? If you're using Python in general, it's just going to make the transformation for you, and it's going to be in the right format. You don't really have to worry about it. If you're using other languages, you're going to have to use the protobuf definition file provided in the AWS documentation to kind of like help define how the protobuf is defined, right? When you do the encoding, when you do this, the transformation. So again, depending on what language you're using, right? Python will work by default. Other languages, you might need to actually include the definition file in order for it to do it properly. Okay. So just some general statements about transformations need to happen. By the way, you can go into the lab and copy down those files, both the tar gzips and the CSV files, if you want to see like what the raw data sourcing looks like, obviously. Even outside, obviously, the visualization. So you can always pull down the data and play with it locally. Now, after pre-processing the data, this is typically when you're going to start the training process. But just to say this first, you might decide to split up your data. Now, as some of you mentioned, you might have a training evaluation set, which is just one set of data, and then a testing data set. Again, depends on what your approach is. For simple holdout, typically what they do is they usually split the training and evaluation or training and validation data. They'll do some training, do a little validate to see are we, head in the right direction. And then once they feel like they've gotten to like the best minimum possible, the difference between the data reality and the predicted reality, then they might do some final testing to check it out, right? So, you want your model to do well, ideally on both the data it already has and data it's never seen before. So this is why, in a sense, splitting your data is important, right? Because you want a portion of your data, right, that the outcome for, right? You want a portion of that data to qualify as like future production data, as almost like your final test. And it's similar to your training data because you want your model to predict a similar, outcome or accuracy has the data that your model has already seen, right? This will help the model to be more generalizable if you have that testing kind of holdout data set. So ideally, right, this is, one way to approach it. So if you evaluate a model with the same data that it trained on, in general, it's going to lead to overfitting, right? Which is discussed later in a module, but really just know that this is where your model has learned the particulars of a data set a little too well. It's kind of memorized it, but it doesn't really actually have a true analysis or a true pattern of the data when a new data set comes in, right? Doesn't perform that well when all of a sudden something it hasn't seen before, it doesn't know how to do it. It's essentially memorized the data, right? So it actually hasn't learned the relationships between the features and the label that it's predicting. So it can't really learn what it needs from the relationships and patterns because it's just memorized the things that it already has. So it can't really apply that relationship, those weights, those parameters to the new data in a way that actually like accurately predicts the outcome. So overfitting is where it does well on the training data, not so great, right, on the test data. Now, a trained model validated against separate data, right? If it does that well, then it's good. Now, just to say this, by the way, underfitting is where it just doesn't do well against any data. Either because the data set doesn't have enough dimensionality to it, there's no like richness to the features, or you've applied too much regularization, like you don't have enough flexibility in the model. So yeah, so underfitting is where it just can't even do its job. Overfitting is where it thinks it's doing its job, but really it's just memorized the data set. And of course, balance is where it's like, oh yeah, we're finding that good, close to reality predictive curve, right? So here's a few validation and testing techniques to think about, right? Now, simple holdout, we've already talked about already. In this case, we're doing 80-10-10. It could be, 70, 15, 15. It could be 70, 20, 10. And, you know, just to say this is that you're going to run several iterations of your model, potentially with different changes in like tuning patterns and whatnot, or different maybe like data augmentation techniques or feature engineering. Hold on just 1 second. Cool. Sorry. All of a sudden I had a phone call ringing in my ear for some reason. All right, here we go. So a simple holdout, right? It's just a common split. So again, the training data, the validation data, and the testing data. So remember that the training data, which is going to include both features and labels, is going to feed into the algorithms. The model is then used to make predictions over the validation data, where you'll start to know where there's things you're going to tweak and change. And then when you're ready to, like, you feel like you're there for that final run, like you're ready to release into production, you run the test data. That test data, by the way, is only going to include features, since you actually want the labels to actually be predicted. The performance you get with the test data is where you can basically what you would expect to see in production. So remember that test data set is unlabeled. Now, cross-validation is where you compare the performance of multiple models, which, by the way, could have very distinct differences, right? Or they could have very subtle differences, which is where I think a lot of people kind of like go with that, right? So the goal behind cross-validation is to help you choose the model that will perform the best in production. Now, so for a small data set, what you might do, this is for small data sets, is you might do what they call k-fold cross-validation, where k is whatever number you want to use, where you get to use as much of the data as possible because you have a small total data set. But you can still get relatively good metrics out of that so that you can basically choose which model is better. Now, with k-fold validation, when you're testing multiple models in different scenarios, you basically are taking the data and you're going to randomly partition it into different validation data sets, right? So for example, you take your whole data set and then a sixth of it would be set aside for validation, but it would be a different sixth every time, right? So you're going to be applying different models to different sixths of this data. And well, in this case, it's actually 5. So fifth, sorry. Obviously I can't read. So this would be like a 5-fold cross validation. So a fifth of the data actually would be set aside for validation in this particular setup. So what would happen is that that segment of the total data set that would be used for validation would be a different set every time. And then you run across the 5 models, and then you would average the results to give you an idea about the performance of the model. So different machine learning models can be, applied to this, training set using this, in this case, 5-fold cross validation to compare the performance. So again, data split into 5 different chunks. One of the chunks is used for validation. Next model run, another set is used for validation. Next model run, another set is run for validation, so on and so forth. So you use all of the training data and you test it on 5 different models with different chunks as the validation portion. So eventually you've tested it on all data points. In this case, k equals 5. This is k equals 8. I'm actually going to count it this time. You're obviously here in this case performing more tests. So there's more model iterations against more segments of your data chunks, but notice that the validation set is actually smaller, right? Someone know like what your, like, anyone do this on a regular basis, what your standard numbers typically are for this? Data scientists typically have strong opinions about the fold. Yeah, Peter, I think that's accurate. 5 used to be really popular. 10 seems to be popular now. Somebody, some people favor 8, but usually, the general recommendation, at least, a while back was it's, either 5 or 10. Typically 10 is preferred now. There's also other like variations, by the way, of this k-fold cross validation. Like you can do iterative k-fold with shuffling, which we'll talk about in a second. So this is what a-fold would look like. One thing to be mindful of is that, you know, when you split your data, obviously, if it's in some kind of a specific order, that can lead to biases, right? Especially if you're working with structured data. So, you know, if, for example, dates or are listed sequentially, that can be a problem. Time denotation, that can be a problem of any type. So your model is going to get used to that structure, by the way, if it is in a time ordered setup. And so the patterning of sequential dates will be learned and it will bias the model. So in this particular case, maybe some shuffling might be useful, right? So it also does depend on the problem you're trying to solve. So just know that if you decide to go with more folds, right, you're going to train the model more times. So you're effectively using the training data all the time. So a larger number here, so like 5 versus 8 versus 10, definitely means more time, right? And more variation in the test error that you're going to get for every subset of the data set, because as you increase the number, the size of the validation test data set is going to get smaller. On the other hand, as the number goes up, the amount of data that you use for training is going to get larger. Because remember, if you're cutting it into fourths, that fourth is going to be a fourth of the data set. If you do tenfold, 10% of the data set is going to be used for validation. So the bias is going to be reduced as the number goes up. So, right, because for a smaller K, like I said, 4 or 5, we're using, you know, a larger chunk for validation, and we're training the model fewer times. So smaller Ks are going to be more biased because you're using smaller amounts of the training data set. So typically, again, 5, 10, you'll see some people favoring 8, but 10 is usually the one that's favored now. Again, this can be varied based on your specific business problem and your needs. So they do actually recommend randomizing your data in the context of this kind of like sequential ordering. They do recommend that you randomize it. Also know that I mentioned this before, is that you could have iterations of your model runs, right? So this is an iterated threefold validation where they shuffle the data, right? So the first time they do it, the data may be left as is, and then they randomize the order of the data for the second iteration, run the model 3 times. For the third iteration, before they do it, they randomize the data again, and then run the model 3 times. The final score is the average of all 3 iterations. Other options for this, for example, could be leave out 1 cross validation. In this one, K is equal to N. So every time you're going to leave 1 data point out for testing, and you're going to leave the rest in as for training data. So instead of splitting it into chunks, you're saying like every 5th data point, we're going to take it out, right? This is used for very small data points where every data point is valuable. I mean, you're still going to end up with a 5th of your data taken out, but it is for very small data sets. Other variations, stratified k-fold cross validation. This is mainly favored when there's like imbalanced data. So for example, if there's like seasonality to the data, like either vacation data or, things around taxes or, items specific like swimsuits or trying to think of like winter coats in an area that has a more temperate climate, right? If there's a seasonality or subgroups in the small group of data, sometimes stratified k-fold cross-validation is going to ensure that for each fold, there's some equal weight proportions for every different fold, right? So that way you might ensure that there's equal representation even when there is going to be one section of the data due to seasonality that has a lot more imbalance in it. So if you want to randomize data before training, right? Obviously in this case, when you do the test split, right? You have an option to randomize the data Obviously, you can set the test size. You can see that in the labs. So you can use scikit-learn to automatically split and shuffle the data at the same time. Questions?
Sorry, I don't know if it's just that my brain is working slowly, but if you're using fewer chunks, aren't you using bigger chunks of the data? A fourth is bigger than a tenth.
Right. Yeah,
So how? Sorry, it's been said a couple times and it's in the notes that if you use larger chunks, sorry, if you use larger K, where is it? You're using a larger chunk of the data. Oh, so smaller K, you're going to be more biased because we're using smaller chunks of the original training data set.
Right.
I don't understand that. If you have K equals 10 and you're splitting the data into 10 pieces.
Okay. So same data set, right? And here, this is 8-fold validation, right? So the size of validate here is smaller. So the amount of total training data that you have access to is much larger. Here, if it's 5-fold, right? Then what happens is that you have a much larger validation section compared to the total amount of data, assuming the same data set. So like if this was 1,000 records, right? In this particular case, if this was 1,000 records and you're doing 5-fold, then you'd have basically 200 for validation and 800 for the remainder of training data. Over here, you'd be using 125 if you're using 8-fold cross validation. And so the remaining, what would that be? 875 would be training data. So you'd see an increase in the training set.
Okay, I think reading comprehension was the issue. The emphasis on training versus validation set.
No, it's all good. You're not gonna hear me throwing any stones. It's all good. Yeah. So it is somewhat counterintuitive when just verbalized, right? So yeah. Okay. All right. So here's an example, by the way, of just simple holdout. No great mystery here. We got our labels on the left-hand side under target. Our split is train, test, and validate. So out of our 6 data point kind of data set, notice that we're taking 50%, right, for training. We're taking another 32% plus for test, and we're taking the remaining 16% for validation. So we're going to use the green and the pink, right, to run our model, and then we're going to do our final production test on the test data. Here is, for example, a 2-fold validation with shuffling. So the first one, notice it's going, well, that must be the first iteration. Yeah, because none of that's shuffled. There should be a second iteration. Yeah, there's a second iteration that's shuffled, right? So here's a 2-fold validation. 2-fold validation where nothing has been shuffled, right? But what's happening here is that we're shifting the test and training data, which portions we're using for test, training, validate. And then the second iteration, we're actually shuffling the data. So it's in a different order from the first iteration. And then once again, we are using different chunks for training, test, and validation. So depending on, obviously this is a 6 data point set, but obviously if it was larger, 5-fold, 8-fold validation iterated with shuffling, right? Good. Okay. So let's talk about then some model training concepts. Okay. So you're actually like, you're ready for model training, and during training, what's happened is that your parameters or weights inside your algorithms have been updated, right? So you want obviously them to be updated in such a way that the predicted reality matches the data reality, which sometimes I refer to as actual reality, but that's not always the case, right? Data reality isn't always actual reality, but you want it to, the predictions to get as close as possible to the actual like data reality. Now, as you know, this can't be done in just one iteration because the algorithm has to learn. It has really no knowledge about how changing the weights inside the algorithm will shift its predictive output closer towards the desired or anticipated or expected value, right? So it's going to watch the weights and outputs from previous iterations and shift the weights to a direction that lowers the error or the difference between what the data reality is and what its predicted reality is, right? So this iterative process is going to stop either when a defined number of iterations have been run as set by you, or it's trending away from minimizing the error and it's actually increasing the error, right? So in general, if the error in the output, the difference between the actual and the predicted reality decreases with each successive iteration, what's happening is that it's converging to, to basically the global, what they call the minima, the global minima, and training is considered successful. On the other hand, if the errors either start increasing or they start changing randomly, the assumption is that something about the model probably needs to be reevaluated, right? Either the size in which it is making changes, because it's probably bouncing around its maximum or its minima, or maybe it's stuck in a false minima, sometimes known as a local minima. So it's mathematically, it's trying to minimize the difference between what it knows is true and what it's predicting is true, right? So how can we can help the computer identify the model with the best fit? So, with like this linear regression model, let's assume you're going to have 1,000 data points and you've got one feature column and one prediction column. They are distributed as seen here, right? Feature is X, prediction label is Y. Remember, during training, it's trying to map between X and Y the simplest way possible. Now, for a human, this is probably somewhat easy to kind of like eyeball, like what would be kind of the in between those points, like the optimal as far as like as close to that kind of scatter of reality as possible. What would represent that general shape? Now, for a computer, this is a little different, right? The loss function, sometimes referred to as the objective function, right, is the measure of the error in your model's predictions given any particular set of weights. Meaning, given the parameters that it has set inside the formula, what is the error that we're experiencing? So it's going to do an output prediction value and the weights calculated up to that point. And the output or the prediction it makes is going to differentiate from the data reality. And the difference between the data reality and the predicted reality, that's the loss function, right? And so it's going to evaluate that loss function over time to make sure that it's going for the minimum amount of loss between, right, what is true and what is not true based on the parameters that it's modifying. Now, there are various ways for this to be calculated, right? For this particular one, for linear regression, the simplest form of loss function in this case is root mean square error, right? That's just the standard deviation of the difference between the observed actual reality from the data perspective and the predicted reality, right? So you just take the difference between the output, the true output, and the calculated output. So the data reality and the predicted reality, you square it, and then you average out across the whole data set. You are not going to have to know this formula. Okay. But you do need to know in general what that stands for. Right? What basically the root mean square error is, right? Difference between the prediction and the actual based on the data reality, you square it, and then you average it out across the entire data set. Another variation of loss function is log likelihood loss, also known as cross entropy loss, right? And instead of raw probabilities of predictions for each particular class, the log of probabilities is considered. So for binary classification in particular, the formula for log likelihood loss becomes this equation, right? where basically Y is a binary indicator of either 0 or 1 of whether the class label, the binary class label, the classification is actually the correct classification for that observation. And P is the model's predicted probability that the observation belongs to that class, right? And the goal here is really just super simple, is that we are trying to get our parameters to change in such a way that they are as close to the data reality as possible with our predictions. Like how it's like, how do we get to the point with the least amount of error? How are the weights updated to achieve the minimum amount of loss in our mathematical model, given that we can turn the dials on these parameters or these weights, right? So how do you find the minima? So optimization techniques generally seek to minimize the loss function that basically quantifies this difference or error as a single value. So just by looking at the graph, you probably know that you want to move your parameters, you want to change your parameters in such a way so you can get to the very bottom of that trough, right? Just has a simple way to look at it, right? With just, 2 dimensions really, right? So that's also known, by the way, as the global minima. I wish this was kind of flipped, by the way, because I think that's more likely to happen instead of what this kind of represents, unless you've got just a huge learning rate, which is a little weird. So imagine we're coming from the right to the left. So imagine you're going along, you're changing parameters, and all of a sudden you see a dip. You see your error, your loss function go down, and you see it go down, and then you keep going, you keep changing your parameters, and you start seeing it go up, and you're like, whoa, I don't want it to go up, right? And so you don't want to keep going because you keep thinking that, you're at the bottom of the trough. And so all of a sudden your error, your difference between your data reality and your predicted reality, you're starting to see the gap widen because you're starting to go up on this trough from the local minimum, right? Particularly right here. You're like, whoa. I was at a low, now I'm going to a high. The problem is that you could just be trapped at a local minima, right? And how do you deal with that, right? Because what you really want to do is you want to be down here at the global minimum, which is the most optimum for that particular data set and that model, right? Given that particular set of weights. Now, with that being said, you could just go slowly, right? You can make small discrete changes over time after every time you run the model and evaluate the loss function every time. But what if your data set's massive? What if it takes you, say this, like, what if every run of the model takes you 6 hours? Now you can parallelize, and there's other ways to kind of run models in parallel. So there's kind of ways around that from a distribution standpoint, but it still can be very inefficient, right? Because we are talking about problems that typically will have millions, if not trillions of data points, again, depending on what model you're approaching and the dimensionality, right? So it can be very inefficient to attempt to find the global minimum by taking all of the possible value combinations of all the different weights and comparing the values. Instead, is there like a mathematical way that we can figure out how to jump down the curve in such a way that lets us know whether or not we're at the global minima or the local minima, or even just do it in a larger chunks based on either the steepness of the curve or the flatness of the curve as we kind of roll through our error rate, right? And this is at the heart of a lot of ML algorithms, right? So notice the starting point, we're making small discrete changes, but it's going to be really hard for us to converge to this global minima without running through a large number of iterations. That can be a challenge. So this is where one of the simplest optimization techniques, gradient descent, right? In this approach, what happens is that the loss function is calculated at that step using that complete data set, and the slope or the gradient of the error curve is calculated using the loss function of the value at like the current point, right? Then like the next point, if you will. So for gradient descent at any point, the slope may point us towards the bottommost point of the surface. So therefore, the weights can be updated, right, by a small step, But if it starts flattening out, then we might jump like with larger like changes in our weights to get to something that starts going up, right? In other words, depending on the slope in question, we might take larger or smaller steps depending on whether we're trending down, whether we're trending flat, and of course, if we're trending up, you know, we might know that we're going in the wrong direction. So that's gradient descent. So as loss decreases, you're going to get closer and closer to the optimal value of the weight. And then notice all of a sudden we start sloping up and it's like, okay, we might be here. And by the way, you might push that in an experiment just to see if you're in a local, you might just like push it past a few iterations and just see how far, because if it starts trending up closer to your starting point, then you're probably there. But again, it depends on how much time you have and how much horsepower you have and how much budget you have and money and et cetera, et cetera. There are boards, especially in Studio, where you can visualize this. You can pull the number out actually, and you can visualize it inside of Seaborn. So yeah, but there's no like, again, outside of SageMaker Studio, when you run the training job, it's not necessarily going to visualize this all for you, Jeffrey. So the minimum is approximated when enough of these operations have been performed to determine that the weights are going to result in the least amount of loss. Remember, the weights are the parameters that we can change, right, inside the formula. So once we realize that we've reached the minimum and things are starting to increase, right? But, you know, imagine the case, by the way, where the amount of change that you make to the weights is so large that you could actually overstep the trough. You could overstep the global minima. So the size of each step is crucial because taking a large step might cause the model to overshoot the bottommost point, miss the global median, and it might be swinging back and forth, never really able to reach the minimum because of the size of changes that it makes, right? This is called the learning rate. These are the size of changes that it can make. If your model is not converging, you probably either want to look at a different optimization technique or at least turn your learning rate down, right? Maybe even set it to a different starting point. So again, if the learning rate's too low, where you're taking baby steps to try and get there, you might have to run through a bunch of iterations. You might run out of time. The business might be like, look, you got 30 days to do this. You're doing 10-hour runs, you know, just as an example. Although, you know, cloud does change some of that. If your baby steps are too low, you're gonna have to run way too many model runs in order for it to figure that out, right? And you might fail to reach the minima in that given time, right? Remember, that step size is called the learning rate. Now, what can instead happen, right, is that you could start out with a larger learning rate and you start to see the loss function shift, right? This is what's going to happen with gradient descent. You're going to see the learning rate slowly taper down, right? So the optimal learning rate is really going to depend on how flat or steep the surface of the error function is. A small value of gradient, meaning it's relatively flat, means the rate could be larger because we could definitely take larger steps down and not necessarily go over the minimum. On the other hand, a large value of gradient indicates that the slope is steep. And therefore, we got to tread carefully because every small movement we make is going to show a really increase, like a reduction in loss. So we don't want to fall off the cliff, right? We don't want to miss the bottom. This is what gradient descent optimization provides us. So the only problem with gradient descent, just like plain old gradient descent, is that it pretty much is going to only update the parameters after it runs through the entire data set. So as a result, updates are going to happen very slowly for large data sets, and it might require a number of iterations through the whole data set for actually to reach the global minimum. So, and gradient descent, you know, like if the data set can't fit into memory, you really can't use gradient descent. So again, you might end up using a larger system size if you want to stick it in gradient descent. Gradient descent also, by the way, will get stuck at local minima, or it can fail to reach the global optimum. So, right, there are ways to change this. For example, you could use stochastic gradient descent or mini batch or other options. What was another option that I was looking at the other day? Anyway, I'll remember here in a second. So there's a couple of different variations. So there's gradient descent, which is going to be the slowest for large data sets. So let's talk about some of the other variations. Then you've got stochastic gradient descent. The only issue with stochastic gradient descent is that every single data point, right? It's like pretty much you're going to update the weights for each record that you have in your data set. So if you have 1,000 data points, stochastic gradient descent is going to update the parameters 1,000 times, right? So with gradient descent, it would only update them once you ran through every single run of the data. So you'd have to run through the data several times. So SGK leads to more parameter updates, and therefore the model is going to get closer to the minima a lot more quickly. However, it's going to oscillate in different directions, unlike gradient descent, but the oscillations are always going to eventually point to the minima, right? Because remember, data points could be all over the place, right? At least when you're updating as you run through the entire data set, it's going to be relatively a lot more smooth, right? There's going to be smoother updates. Whereas stochastic gradient descent, as far as like if you plotted it, it's going to be, bouncing all over the place as it approaches the minimum. Now there is a kind of a, oh yeah, this is the same thing I just said. There's a kind of a happy medium that you could explore, which instead of updating weights in the formula at every data point or updating them after running through every single data, the entire data set, you could actually just define a batch size and say, look, instead of doing every data point, how about, every like 10 data points or every 20 or 100 or 1,000, right? You could do updates. So it's less noisy and erratic than stochastic, but it converges quicker towards the minima than gradient descent does. So you can define the batch size, by the way, which also will make it easier because remember, gradient descent, requires the entire data set to fit in memory. With mini batch gradient descent, you can actually put that smaller data set. So you could calculate what you could stick in memory at that point in time. All right. So these are all commonly found algorithms in SageMaker, right? And we are going to talk about running training jobs, and you're going to actually run some training jobs, especially in the next lab and the lab after. So after we do evaluation, which will be, I believe, tomorrow, then you're actually going to run the training jobs and then do some evaluation and some, well, you will save tuning for the last day, but yeah. Questions about gradient descent, stochastic gradient descent, or mini batch gradient descent? And yes, these are all on the exam. Particularly this section right here, I probably would know this, just memorize this particular slide. Cool. Let's see. We only got a few minutes left, so I'm going to pause actually right there before I step into this next set. We're going to talk about training, or like running training jobs. By the way, this is the one, Darche, where it talks about using built-in algorithms versus using your custom script on a supported framework versus bringing your own everything with a Docker container versus using a Docker container from the marketplace. So we'll cover this tomorrow. I just want to make sure you knew. Okay. Questions about anything I've talked about prior to this? Okay. All right, so let's talk about that spreadsheet that I posted in earlier. So, because we're going to switch to test prep here. So let me stop this.